Hi everybody, this is Mr. Nolan, and you are watching video 3 in the series Finding Molecular Shapes. The goal of this series of videos is to be able to predict the structure of a molecule based on its formula and the periodic table trends. If you did not watch the first video in this series with the periodic trends, please go back and do that. You'll find the link in the informational section of the video. But ultimately we want to be able to figure out how do we build a molecule based on the atoms that are there. We're going to be doing all hydrocarbons in this video, so these are kind of advanced, relatively advanced for where we need to be, but they're also pretty fun to do. Before we go any further, please, I implore you, pause the video and sketch these down on a piece of paper and give them a shot. For each one, try them. Have an eraser ready so that if you make a mistake, you can go ahead and go back and try to fix it. These are very much trial and error situations where you have these structures, you're trying to figure out how do I build these structures. And so don't feel like if you do it the first time and it's wrong that, you know, you're doing a terrible job. You just have to kind of have some perseverance and keep at it. So let's do number 1 here. I'll open up my screen sketch. And what I said earlier in a previous video is that hydrogens are kind of like the petals of a flower, and they'll be found on the outside of the molecule, like petals of a flower. Whereas the carbons and also nitrogens are going to be found kind of toward the middle of the flower because they can form many bonds, whereas hydrogens can only form one. So you'll only find hydrogens on the outside. So if we look at example 1, this is called ethane. And I'm going to go ahead and I'm going to take my 2 carbons. Because I can only bond hydrogens once, there's no way I can get these carbons in the same molecule without bonding them together. So those 2 carbons are going to be bonded. And let's just go ahead and array our hydrogens around the outside. Once we do that, we'll just go ahead and bond them. Okay, and once we do that, all we have to do is just double check each one to make sure that we have the right number. So that hydrogen, all of these hydrogens have exactly 1 bond, and so that is correct. And the carbons have 1, 2, 3, 4 bonds each, and so that carbon's good. Carbon 1, 2, 3, 4, so that carbon is good. So this is what ethane looks like, and this is in fact the only structure that you can create for molecule number 1. Okay, so this is example number 1. 2. This one's a little different. This is called ethylene. And what's interesting about ethylene is that this is actually a hormone found in plants. And if you take apples or bananas or oranges or tomatoes or something and put them in a bag, they will produce this gas, ethylene. And this gas is what actually causes them to ripen. So it's sort of interesting. It's called ethylene gas. So let's kind of take a look at how we would build this. Let's put our carbons in the middle, like we just did for number 1, and they're probably going to have to be bonded. But notice we have a difference in the number of hydrogens. We only have 4 hydrogens as opposed to the 6 up here. So how are we going to deal with that? Well, let's just array them around the outside, just like we did before. And we have noticed right away that, well, I only have 4. I'm out of atoms, so I don't have anything else I can do here. So there's a few ways that you might approach this problem. This is one. Well, let's take that carbon, let's bond it to everybody that we can, and then maybe bond this carbon to that one. But you notice that we have a problem here. There's one big issue, and that is that this carbon right in the middle is not observing the periodic trends. Carbon is supposed to have 4 bonds, not 2, like we observe here. So that carbon is incorrect. There's no way that we can make this molecule work if we're going to attach all of these hydrogens to that carbon. So I don't think that's going to work. So instead, what we need to do is we need to figure out how can we make this molecule fit. Let's just keep playing around. Now, if you do keep playing around, what you will find works best is this. Attach 2 hydrogens to that carbon, attach 2 hydrogens to this carbon, and then attach those carbons together. Now, we still have a problem. Each of the carbons only has 3 bonds. It's supposed to have 4. And so we're out of atoms. We don't have any more atoms to add. So at this point, if you are out of atoms and you can't add any more, but you need bonds, just add them, right? So now, if I go ahead and look here, I take a look at each carbon. This carbon has 1, 2, 3, 4 bonds. That's good. And this carbon over here has 1, 2, 3, 4 bonds. That's good. This is ethylene. It's a double bonded. It's an alkene. Let's look at number 3. 3 has another what's called a degree of saturation. This molecule is interesting because it's what is used in really high power torches. It's called acetylene. So you might have heard of an acetylene torch. This is the molecule that's used in an acetylene torch, and it has a very special bond. It's got a very, very powerful 3 lined bond. So let's kind of figure out what this looks like. Again, I've got my 2 carbons. They're probably going to be bonded, and I need to put my hydrogens around the outside, but ooh, this is kind of a strange situation. I've only got 2 hydrogens. Well, let's go ahead and bond those. But we're not finished. If you were to stop here, you would recognize that these 2 carbons are not finished, because they need 4 bonds, and yet they each only have 2. Well, what I just told you in example 2 is that if you run out of atoms like we just have, and you need bonds, just add them. So just add a bond. So now, if you look at each carbon, while they're still not perfect, they only have 3 bonds, but at least it's closer. Let's go ahead and add a 3rd. Or a 4th, rather. So now, in this situation, each carbon has got 4 bonds. There's 3 bonds between them, 1, 2, 3, and then each carbon also has 1 bond sticking out to the side. So this is now finished. This is called acetylene, and this is the only situation that will work for this one. If you were to try something along these lines, you would find that this doesn't make any sense, because hydrogen can only form 1 bond, not 2, so we're not allowed to do this. Instead, we're supposed to have that. So that's what acetylene looks like. Very high-powered torches. Let's go ahead and jump down to 4. 4, oh, this is increasing in complexity. We have C3H8. So let's go ahead and figure out how to do this one, C3H8. So I've got 3 carbons and 8 hydrogens. So I'm just going to go ahead and put my carbons in a line, or maybe something like this. Maybe I'll do this, put them kind of in a triangle. And my carbons, because I've got my 3 carbons, they're definitely going to have to be connected together. They're the only atoms that are in this molecule that can bond multiple times. So they're going to have to be connected together in some way. And I've got 8 hydrogens. And so I need to figure out, well, where am I going to put these 8 hydrogens? Well, let's stop right away before we even go any further. This carbon in the middle has already got 2 bonds occupied. 1, 2. So this carbon only needs 2 more bonds, and it's going to be full. So let's try that. Let's just fill it up. Fill up the rest of the bonds that carbon can make with hydrogens. So that carbon is bonded now 4 times, right? 2 hydrogens. And if you look at the remaining carbons, well, we've already used, 2 of our hydrogens. We've got 6 hydrogens left. And look at that. We have 1, 2, 3, 1, 2, 3 spaces that you can use to fill these carbons with bonds. So let's go ahead and do that. So if I put my hydrogens on the outside, I know this is drawn a little janky, but I think you kind of get the idea. We have these, I'll choose orange here. We've got these carbon-carbon bonds. There's our 2 carbon-carbon bonds. And then we've also got all these carbon-hydrogen bonds, which are all around the outside. Again, notice the hydrogens are on the outside of this molecule, kind of like the petals of a flower, not on the inside. And so this is called propane. And propane is what, your mom or dad uses to cook stuff on the grill. If you compress it under high enough pressures, it will actually become liquid. So if you've ever heard of LP gas, that's liquid propane gas. That's the big gray tank that you'll find under your gas grill at home. So this is the only possible structure for propane, and this is it. Let's do this last one, number 5. What we're going to find is there's actually 2 different ways to draw 5, and as long as you recognize that either one of these 2 will work, then we're good. So if we look at 5, the thing we notice right away is that, like 4, it's got 3 carbons, but we're missing a pair of hydrogens. Now, when you get into organic chemistry, what you'll learn is that that's called a degree of saturation. Because we've lost a hydrogen, but we have the same number of carbons, I think that we're going to have some double bonds in there. Kind of like how up here we had C2H6, and when we went to number 2, we found there was a double bond. That double bond squeezed out some of these hydrogens. Then when we moved down to 3, that triple bond squeezed out another pair of hydrogens. So if you notice this, you probably might have some double bonds or triple bonds. So let's look at 5. So C3H6. I'm going to start the same way that I did before. Oh, look, we're in orange now. Okay. C3. And H6. So I need my 6 hydrogens instead of 8. Well, this kind of presents us in an awkward situation because we only have 6 instead of our 8, so we can't build it the same exact way that we did before. So I suspect we'll have a double bond in here, but let's go ahead and wait and see. So, whoops, I want black here. Okay, so let's go ahead and take our hydrogens and just kind of array them around the outside, and let's just kind of see what happens. Okay, so I've got my hydrogens all out here. Let's figure out how we're supposed to bond these. So here's one way you can try to do it. You can try to bond 2 hydrogens to each carbon. Okay, so those are all bonded. And let's just go ahead and bond that carbon to that carbon. So this carbon up here is satisfied, but these 2 carbons are not. So here's one way that you can solve this problem. Just form a cyclic hydrocarbon. So this is actually an example of cyclopropane. So we have our 3 carbons, and they're actually bonded together in this little triangle. And if you look carefully at each carbon, they each have 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Pretty exciting. So we've actually solved this one very, very easily without any double bonds, just by forming a cycle, forming a little circle. Now that's a little advanced. I wouldn't expect you to be able to figure that out on the first try, but if you play around a little, that is one solution that you can come up with. So that's one solution. But there's another solution here too. There's one other thing that we can do. Let's go ahead and take our carbons. I like that orange. We'll go ahead and stay with orange. We've got our carbons. And let's see if a double bond plays in at all. So we've got our carbon, carbon. We've got our hydrogens. Let's just kind of start arraying these around the outside. I'm going to save one of them. Now, if I go ahead and throw in a double bond, let's say, I don't know, a double bond right here. Now this carbon, if I attach that carbon to those 2 hydrogens, that carbon's done. Now this carbon is finished. This carbon has 1, 2, 3, 4 bonds. This carbon over here has also got 4 bonds. 1, 2, 3, 4. This carbon has only got 3. So if I add my remaining hydrogen, let's count up, make sure that we're good. 1, 2, 3, 4, 5, 6 hydrogens. There we go. And our 3 carbons. So this double bond, by the way, this double bond could go here or it could go there. It doesn't actually, well, I guess it does kind of matter how you set it up. If it was to go over there, what you would have to recognize is that now you have to move a hydrogen from here to there. So you could have this situation or you could have this situation. So either one of those would actually work. So I hope that this video has been helpful in figuring out how to form the structures based on the molecular formula and the periodic trends. For some nitrogen examples, go ahead and look at Finding Molecular Shapes 4. And until then, happy science.